From next video onwards, we will be solving problems based on the concepts discussed in this video. And the first concept is Pfaffian differential equation. Pfaffian differential equations are equations of the form sigma I equal to 1 to n f of I dxi equal to 0. So pause and read what's written in the screen. Though it looks complicated, it is fairly simple. And we will be mostly dealing with cases where n equal to 2. That is, it will be of the form shown in example 1. M dx plus n dy equal to 0, where m and n are functions of two variables, x and y. So here the dx of I, right? So when I equal to 1, that is for first function, it will have dx of 1. That is d of first variable. Here we have two functions and two variables x and y. So d of first variable will be dx, and for second function it will be d of second variable dy. So m dx plus n dy equal to 0. And when n equal to 3, we will have three functions p, q and r. Each function will be functions of three variables x, y, z. And here it will be d of first variable dx, and for second function it will be d of second variable dy, and for third function it will be d of third variable, which is dz. So p dx plus q dy plus r dz equal to 0. So this is Pfaffian differential equation, and as I said before, we will be dealing mostly with n equal to 2 form. So m dx plus n dy equal to 0. So next concept is exact differential equation. So exact differential equations are differential equations of the form m dx plus n dy equal to 0, and which satisfy a certain condition. That is, if the given equation is called exact if there exists a function f of xy such that differential of that function is m dx plus n dy. So if this is differential of f of xy is equal to m dx plus n dy is true, then we can say that m dx plus n dy equal to 0, the given equation is an exact differential equation. The exact differential equations comes very handy, because once we show that the given differential equations are exact differential equation, finding solution for such differential equations becomes very simple and straightforward. So I will show you how. So I'll just write down why finding solution is very simple. We have a differential equation m dx plus n dy equal to 0, right? So we need a solution which satisfies what is a solution? Solution is one when substituted in this differential equation reduces it to an identity. That is, it should satisfy this equation. Differential of that solution should satisfy this, right? So say it is an exact differential equation. That is, we have f of xy such that d of f of xy is nothing but m dx plus n dy, right? If this is true, then we can write the solution as f of xy equal to c. So this becomes automatically the solution to such differential equations. Why? What do we get if we differentiate this? What do we get if we differentiate this equation f of xy is equal to c? We get d of f of xy equal to 0, right? What is d of f of xy? as per our definition, it is mdx plus ndy equal to 0, which is our differential equation. So this is a solution. This becomes a solution, right? So once we show that the mdx plus ndy is equal to 0 is an exact equation, then solution, writing a solution, uh, exact equation where there exists a function f of xy, then writing solution to such differential equation become straightforward and easy. And the next question will be how to find this f of xy, right? Given mdx plus ndy equal to 0, how to check whether this given equation is exact or not, and if it is exact, how to find f of xy. This is the uh, question part of this concept. So questions will be asking to check whether the given equation is exact or not, or it will be straight away asking for the solution. And if we are able to show that the given differential equation is exact, then we can easily say, since this is exact, uh, uh, the f of xy, which can be created in a particular way, which we will see in the next slide. And if once that we write the f of xy, we can write f of xy is equal to c is a solution to such differential equations, such differential equations. So this is the question part. This is how our questions will be. It will that is, it will be of two type, either to check whether the given equation is exact or not, and to find the solution for such exact differential equations. So there is so first, to check whether the given differential equation is exact or not, there is a necessary and sufficient condition, which is dou m by dou y equal to dou n by dou x. That is, we will be given mdx plus ndy equal to 0 form differential equation, right? From that, we can identify what our m is and n is. Once you identify what m is and n is, you can check whether dou m by dou y, that is partially differentiating m with respect to y, is equal to dou n by dou x, partially differentiating n with respect to x. So if this is equal, then we can say the given differential equation is exact. So remember this condition. It is both necessary and sufficient condition. So if you are interested in the proof why this condition is both necessary and sufficient condition to check exactness of the differential equation, this I have condensed the proof into few lines. You can pause the screen and read if you are interested. And if these steps are not clear enough, just take any standard textbooks and you can easily find the proof. Or if you want me to do a proof and discuss that in another video, do comment. Otherwise, I'm not going to discuss the steps. Just pause and read. It's fairly straightforward. Okay. Then just remember this necessary and sufficient condition to check exactness. Then the working rule for solving an exact differential equation. So once we have our equations, we will check dou m by dou y equal to dou n by dou x and see if it's exact. And if it is verified that it is an exact differential equation, then we can write solution as integral m dx. M is a function of x and y, but here integral m, in this first part, we treat y as a constant. So integral m dx plus integral terms in n not containing x. So n is also a function of x and y, right? If it has three terms like x square y plus y cube plus 2y, something like this. So I randomly created an n which is of this form. So second part of the solution, second term of the solution is integral terms in n not containing x. So in this case, this part contains x square x right, x square y. So this does not contains y. So we can write in integral y cube plus 2y dy. So that is what terms in n not containing x means. So integral m dx plus integral terms in n containing x dy equal to c is the solution. What is this? This is nothing but this whole part. This is nothing but f of xy, which we discussed earlier. So we said there for an exact differential equation there exists an f of xy such that differential of f of xy is m dx plus n dy, right? This is our f of xy. So you can see that in this sufficient the sufficient part, in the sufficient part we create an f of xy for a general case where dou m by dou y equal to dou n by dou x. So we assume that this is true, and then we create an f of xy where g of xy is integral m dx only. So plus n of n minus dou g by dou y dy. So we create such an f of x and show that there exists such an f of xy if this condition is true, dou m by dou y equal to dou n by dou x, there exists such an f of xy and the equation is exact. So here, so in solution also, as I mentioned earlier, this is the f of xy part. So once we have this f of x, the solution for f of an exact differential equation will be f of xy is equal to c. So this is what that is written here. So integral m dx plus integral terms in n not containing x dy equal to c. So this is the solution to this is the solution to any exact differential equation. The question will be asking for solutions. So first we check whether it is exact and write solution as this. So if all this is too overwhelming or confusing, just start solving problems based on this concept and you will have a better understanding of the concept and will have a clarity how to solve such problems. So okay, these are the concepts. Then I will just quickly recap what we discussed in this. Sorry, let me just clear this. Okay. So what we discussed is what is Pfaffian differential equation, differential equations of this form. Then we saw two examples of Pfaffian differential equations where n equal to 2 and n equal to 3. Then we saw what an exact differential equation is and the definition of exact differential equation. Then we saw the necessary and sufficient condition for a differential equation to be an exact differential equation. Then we saw working rule for solving an exact differential equation, how we can write a solution given we have shown that the equation is an exact differential equation. So these are the concepts and we will start solving problems from next video onwards.